Um, uh, can you see the whiteboard?
Yes, sir.
Okay, so this was the problem that we were discussing in the last class, and I went out. Now, let us sort of move ahead. And did you people solve this problem, or did you not solve it? Let us, for example, as I said, choose values for D in minute inverse. Let us say 0.1. Just too fast, but anyway, or let us say 1, 2, 3, 4, 5. Let us say that we have this. Oh, it started trouble immediately. And let us have some data here. And let us have some first S naught. Let us say what? Let us put some numbers. 50 millimolar input. Let us call this 50 millimolar, and we get output S out. And we have some. And let us say that we know the Vmax. How will you know the Vmax? I hope you know how we will know the Vmax. What is Vmax? Yeah. Suppose you know the K-cat. The K-cat or the turnover number. Can you find out Vmax? Or you don't remember these things? What is turnover number? What is K-cat? What is K-cat? K-cat is also K2. And if it is simple Michaelis-Menten kinetics, V is equal to Vmax S upon Km plus S. What is Vmax in terms of K2? It's equal to K2 into E naught. Now, if you know the amount of enzyme that has gone inside, and if you know the weight of the beads, then theoretically you can find out E naught, because this is the E total. And so that into K2 will give you your K-cat, and you can know your Vmax. Right? And from this, we can now move ahead and write the basic equations as simple enough as what? As D S naught minus S is equal to V is equal to Vmax S upon Km plus S. Notice that I know Vmax. Now, how would you find out Km? Km has to be found out in a least square sense. If I have just one data point and I know Vmax, I can do it. If I have just one data point. Otherwise, it has to be found out in a. If I have one data point, then I can write, for example, whatever, 1 into 50 minus S, and suppose this is at 1, suppose this is 20. And suppose at what would it be at higher dilution rates? Outlet concentration, will it be higher or lower?
Sir, I think it will be lower.
अच्छा, क्यों लगता है आपको?
Because sir, as dilution increases, as
dilution increases, what increases?
concentration will decrease, sir, no?
आपको लगता है concentration decrease हो जाएगा?
Sir, we dilute 2 times.
ये dilution rate है, ये F upon V है. Flow rate per unit time, right? I hope you know this.
Yes, sir.
So what is the basic equation? D S naught minus S is equal to V. Do you follow this equation, or is it not clear at a steady state?
It is clear.
I hope
Sir.
you know this, right? Huh?
Yes, sir.
D ds by dt is equal to coming in Fs naught minus Fs out minus amount consumed by reaction, which is equal to Vms, and this S is S out for ideal CSTR upon Km plus S out. Do you follow this? And this is 0 for steady state. So F is equal to this into V, of course, volume. And so we get this F by V, and this equation translates to this equation. Is this obvious? You're familiar with
Yes,
this?
sir. Yes, sir.
Okay. Now tell me, how would the plot look like for different dilution rates? Suppose I give you the values of Vm and Km. Suppose I give you the value of Vm and Km, and I mean, let us do it very, very slowly, because I think we have serious issues here. I do not know, somebody has taught you improperly or properly, I do not know. Suppose I know Vm and Km. Suppose Km is 5 and Vm is 50. And Vm, I don't know, let us put some numbers, random 50. So what do we get? 1, 50 minus 50 millimolar was then in feed, and kbm is also, let us take bm as something different, so that we know 20 let us say 20 millimolars per minute. 150 minus s is equal to 20s upon km is 5 plus s. Second, 250. Can you, for example, now tell me what will be the value of s? Add 250 minus s is equal to 20s, 5 plus s. This is s1, this is s2, 350 minus s. Solve any one of them. 20 s1, 20 s2. Solve the first one. This is 1 into this is 2 into this is 3 into this, and tell me. Okay, let us solve the first one. Let us do it, because I believe that we have to get down to basic algebra before anything else is done. More serious, complicated jobs are done. That is why the reasons for examination performance being what it is. What is the solution? So 15 minus S1 into 5 plus S1 is equal to 20 S1. That is one way to do it. So what is S1? Can you please solve it for me?
Sir, it's 17 by 2. 17 by
Huh?
5. It's
How much
coming
is it?
around 8.5, coming around 8.5.
8.5.
Yes,
So
sir.
could you
17 by 2.
could both of could both of so S1 is equal to 8.5. Is this what you are getting?
Yes, sir. My
What
loans, sir.
about S2? And what about S2? S2 will be 50, 50 minus S2 into 5 plus S1 is equal to, now divided by 2, so that's 10 S1. What do you think you will get? 10 S2, sorry. S2, S2, S2. And what will S2 be equal to? I will wait for you people to answer. Hello. Can you do this?
Yes, sir.
Yeah, do
Yes,
it,
sir.
please. Kariye.
Sir, it's 41.5.
Approximately.
13.
Huh?
11.5.
So do you realize that as you increase the dilution rate, your S out will go up, not
Yes,
go
sir.
down. The reason for that is obvious. As you're increasing the dilution rate, your residence time is declining, right?
Yes,
The
sir.
time that you are providing is declining, and if you're providing less time for decline, then S out, then P, the product formed, will decline because time is less, and P product formed is nothing but S naught minus S. Right? So if the product form declines, then S increases. So the unconverted substrate will tend to increase as you reduce the time available for reaction. So only when you give high amount of time will you get full conversion. Otherwise, you will not get full conversion. Right? So this is the point that you need to understand, a rather simple point, that or else you can take this expression here, and suppose you would suppose the reverse problem was there, which is usually the case, that S values are known and you have to find out Vmax and Km. Now how would you do that? You would obviously take the inverse just like that, Km plus S upon, rather than solving it again and again for different values, upon Vms. What does it become? It becomes is equal to 1 upon dP. Right? Do you follow this argument?
Yes, sir.
Okay. Now, therefore, if you want to find out Km and you know your Vmax, otherwise also let us forget it. Let us suppose you don't know them. So you write Km the same. You do the same method. Km by Vm into 1 upon S. Please go ahead. Plus 1 upon Vm is equal to 1 upon dP. Right? You follow this argument?
Yes, sir.
So
Yes,
now when you know S out, you also know P, because S out is nothing but S naught minus S. This is here. And you know your dilution rates. So you know S, you know S out. Can you now use this graph to plot something that will allow you in a least square sense, allow you to find out Km, Vm and Vmax? Right? यहाँ पे instead of 1 by V, so notice that instead of 1 by V, you have just 1 upon dP, which makes sense because V is nothing but D into P. Do you understand? V is nothing but D into P.
yes, sir.
Yes, sir.
Obviously, dilution rate into product. So velocity is nothing but inverse product. What is velocity? Rate of product formation per unit time. P into D per unit volume. Isn't it?
Yes, sir.
So that's rather
Yes.
obvious. So therefore, these things you should. I mean, these are I thought very obvious, but anyway, I'm sort of repeating this because there is no other way to go about it. These things are repeats of what we have done. So essentially, from a plot of velocity of 1 by v, which is also the same as 1 upon dp, you can plot this versus 1 upon s. So you can plot 1 upon s, which is actually the s out here, the s out here, versus 1 upon dp. अरे भाई क्या है? upon dP, which is velocity, and determine both Km Vmax and 1 upon Vmax. And if you know your Vmax, first of all, you should check your Vmax whether they are matching with the, if you know your Vmax. If actually Vmax is the same, then hopefully it's an error. If Vmax has changed tremendously, then you are in trouble, because then you have to say that, hold on, my Vmax has changed because the process of immobilization has distorted the enzyme. Now, that's a more complicated problem. I'm not going to get into that. Okay, sometimes the process of immobilization may actually change Vmax because it may change Kcat. Kcat would change, the ability to catalyze reactions would change if the enzyme shape is got distorted because of the binding process. If this has got distorted because the enzyme is bound here and the active site is here, then that's a more complicated question. That is a question we are not going to answer. Okay, so we will assume that Vmax and Km are as per the original enzyme. You know, there is no change of Vmax and Km. Intrinsically, the enzyme remains the same. Therefore, Vmax should not change. But as we plot this graph, we also notice from this plot that you are going to get into very interesting situation where the Km would effectively change because the enzyme is now trapped inside, and assume that the enzyme intrinsic properties have not changed, but the substrate concentration here may be some S, which is the S out here, which this is the S out, right? But the concentration here is quite different. So as you go along the radius of this sphere, which is the immobilized enzyme, this here is S out, which is the concentration here, S out, but inside the sphere, the concentration may well be like this. And therefore, the effective reaction rate of this system is because of immobilization or internal mass transfer control. Now, how does that work? Again, problem. So now, do you remember your internal mass transfer equations? So now we have solved the basic CSTR equation, but we are stuck with the internal mass transfer issue, because this S out, if this S out is this, it will be like this. But suppose the S out is somewhere here, maybe it will be like this. And something else, something here, it will be something like this, whatever. So which of these? And every time the efficiency will change. And efficiency is a measure of what would it be in the absence of mass transfer and in the presence of mass transfer. So if efficiency is changing, your V is changing. Real V, actually. So how do you then predict what is happening? We have now understood to handle the CSTR. Why did I choose a CSTR in the previous class? I chose a PFR because CSTR has no external mass transfer control. Because of the mixing, there will be no sort of film out. The convective mass transfers are very good, right? So there is no film. So there is no diffusion control because convective mass transfer ensures that the surface concentration here is S out. If I had a film, then this bulb would be S out, but this here would be something else, which would be external mass transfer control. So we are ignoring external mass transfer control, but we cannot ignore internal mass transfer, especially if the enzyme is embedded inside. So now tell me, how will you solve this problem? So now suppose I will now jump, because I don't want to do this arithmetic all the time, and you can find out Km by a much more graphical method than by solving quadratic equations hundreds of times. That's not a good idea. So you were solving quadratic equations. I'm sorry I made you solve it, but that is because you should remember that originally it could be simply solved by solving a couple of quadratic equations. But let us assume that we don't have to solve quadratic equations, and suppose, or if we have just one data point, then obviously you will need to solve a quadratic equation. If you are node VM and you know that at dilution rate of 0.1 or 1 or whatever, you know your P out, which is nothing but S naught minus S, whichever, you know either S out or P out, and you know this number, some P1, then obviously if you know Vmax, you can calculate Km. But this Km is now has to be understood in terms of the fact that there is internal mass transfer diffusion. So this Km is the Km apparent the Km apparent, which is must be larger than the Km true. As I said, we are assuming that the Km true value and the Vmax are not impacted, but Vmax does not change. So the graph, instead of being like this, is like this. Okay, so this is the original unbound enzyme. And after doing the kinetics with this enzyme in a CSTR, you discover that this is kinetics like this. So this is simply saying that Vmax is the same at large values, and this is S, this is V, but the half of Vmax is Km apparent. So Km apparent is much larger. The apparent Km apparent is obviously much larger than the Km true, where this is what you will measure experimentally. Are you with me till now?
Yes, sir.
So now tell me, from the studies that we have done, how will we move further ahead? So now let us go back and think about how we derived our equations. How did we derive our equations? So we derived our equations by saying that the rate, I hope you remember this, that the effectiveness n eta was when phi was greater than 20, eta was 3 by 5. Remember this approximation?
Yes, sir.
So eta was 3 by 5 when phi was greater than 20. And so what does that make it equal to? And what was phi? So this is equal to, बताइए, अब आप लोग थोड़ा सा अपना टेक्स्ट देखिए. So is 3
by
upon
5
R d by K1.
Yes, sir.
When K1 was the first order reaction. ठीक है? याद आया ये डेरिवेशन आप लोगों को?
Yes, sir. Yes, sir.
हाँ, क्योंकि आपको मैंने phi square का डेफिनेशन बताया था. Phi square was for first order reaction for any order K CAS n minus 1 R square upon D. याद है ये एक्सप्रेशन? ये तो याद होगा. तो for n is equal to 1, है ना, ये CAS डिसअपियर कर जाएगा. ठीक है ना? तो KR स्क्वायर अपॉन D, तो 5 हो गया. मैं बार बार डिराइव कर रहा हूं. R root K by D, K1 by D, when K1 is the first order reaction constant. So when 3 upon 5 will become 3 upon R root DE by K1.
Root D by K. Yes, sir.
ये तो क्लियर है ना?
We have done this before in class.
So now, yeah, when you've done this before in class, now tell me how to solve this. How to solve the CSTR problem. इसका फायदा क्या हुआ जब आप इसको क्लास में करने का फायदा क्या हुआ? तो रेट क्या हुआ फिर आपका?
3 by R. 3 by R.
3 by R.
Root D K1.
D by K1 into K1 KAS, right? CAS.
Yes, sir. K1 CAS.
ठीक है ना?
Yes, sir.
ठीक है ना? So which becomes what? Which becomes what?
3 by R. Root.
Whatever. 3 by R.
Root D.
Root D.
K1.
K1.
No, sir. D K1 only. Not this.
हाँ, ये अंदर आ जाएगा ना, ऊपर आ जाएगा K1 into CAS.
Into CAS, yes, sir.
Obviously into CAS. But now look at this reaction here. What is the value here? As S tends to 0, this becomes first order reaction. And as S tends to 0, remember I pointed out that phi will become greater than 20. The phi will keep on increasing. At lower and lower substrate concentration. This I proved in the external mass transfer, but I hope I don't have to prove it here again. As you lower the concentrations of substrate, do you follow this argument? as you lower the substrate concentrations, A, it becomes first order, B, it becomes more and more internal mass transfer limited. Remember this argument that I gave you in the last class also, that
Yes, sir.
when your V values, when your S values are high, and this is V versus S, and you have S in the surface of the bead as some value here, then even if the surface concentration because of mass transfer drops from here to here, I have no significant drop in the velocity. So the internal profile of substrate concentration drops from 0.1 to 0.2, but notice that all parts of the bead have the same velocity and therefore efficiencies are close to 1. Right? So this is reaction rate controlling when phi is very small. Phi is small. Remember this graph? Phi is small. But when I go here and it drops from here to here, notice that there is tremendous drop in efficiency at first order. And phi is greater than 20 because your phi values are very large. Because this is mass transfer control. Because outside of the bead, this is the concentration, you are seeing 1, and inside of the bead, you are seeing 2. And as you go down and down with S, phi becomes larger and larger, and it becomes more and more first order. So therefore, in the limit, I can take this slope. And what is the reaction rate when S is very, very small in terms of first order? It is nothing but this tangent. Correct? It is a first order reaction with a tangent. And what is the derivative? What is the derivative? The derivative of this is, I hope you know this, V is equal to V max S upon Km plus S, which is nothing but, when S is much larger than Km, is nothing but Vm by S is much larger than this. Sorry, okay, Km is much larger than S. So we can write this as only upon Km. So your slope is, I hope you realize this, this is equal to, come on, this is equal to V max upon Km apparent into Cas, first order
Yes, sir.
reaction.
Yes, sir.
Oh. So Cas and Cs will cancel out. And so you have this basic expression. Okay. So the Km apparent and the Vmax, which you have determined from your CSTR studies, are now going to allow you to determine DE and K1. Because what is K1? What is K1? K1 is the first order reaction constant of the ordinary enzyme.
Yes,
if
sir.
there was no mass transfer, because, right? Are you following this?
Yes, sir. Yes, sir.
Yeah, so therefore K1 is nothing but, so therefore 3 by R root DE, K1 is nothing but V max. Oh no, I've gone out. Can you hear me?
Yes, sir. We can hear you.
Okay, so 3 by R DE, and what is K1? K1 is V max upon Km true at low concentrations, isn't it?
Yes, sir.
And this is equal to what? This is equal to V max upon Km apparent. So notice that the change from Km true to Km apparent is what is going to help you determine the parameters DE and V max and DE if you know your radius. So suppose I'll just put some numbers just for you to calculate. So now this basic equation now allows you to determine DE. And for example, you can now have a problem like this, that suppose the rate is known to you. Suppose, I mean, I don't know. I mean, let us say that you can find out Vmax by Km apparent. I mean, let us choose some numbers here. Let us say the diameter of beads is 3 millimeters. Okay, so then R is 1.5 of course. ये थोड़ा गड़बड़ हो गया, चलो कोई बात नहीं. So so 3 by 1.5 root DE, and let us say what was the value. I said suppose I found out that that Vmax was 20. Remember 20 पुराना वाले ले लेते हैं, and Km apparent हमने discover कर लिया. Km true was 5. Km true was 5. Remember that is what I chose. Just so D into, so what do you get? DE 20 by 5 and so on and so forth is equal to, let us say we find out the velocity. I mean, and that is Vm by Km. So Vm by Km was 20 was the velocity, and suppose we find out Km apparent as something, right? Km apparent, let us say it is 30. So it is 20 by 30. So what is DE equal to? So 2 root 4 DE is equal to 0.66, right?
Yes, sir.
So 4 बाहर आ गया, ये 2 बाहर आ गया, तो 4 root DE is equal to 2 by 3, and so you know what is DE equal to? Something 1 by 36, right?
Yes, sir. 1 by 36.
हाँ, 1 by 36. 1 by 6 हो गया, ये 1 by 36 हो गया. 1 by 36. So you now know your DE. Now, for example, I can ask you the question that I used R, I can't change it. I use 3 millimeter beads. What would be the output when you use 2 millimeter beads? Now you know your D. So you can find out your Km apparent, and you can tell me at D is equal to a dilution rate, not D. Remember, at D is equal to 0.2. If my output is this much at 3 millimeter beads, you can tell me what will happen at 2 millimeter beads or 1 millimeter beads. You understand?
Yes, sir.
So that is the power of this technique. The power of the technique is that you measure it at 3 millimeters or 4 millimeters, but suppose you are asked by industry, well, can you make smaller beads, and how much improvement will I get if I made smaller beads? And you can tell them, yes, yeah, that is a problem. That is a doable problem. So is this clear?
Yes, sir.
So can I stop here? Yeah. And of course, now, and let us not get into more complicated stuff, but I suppose you can understand that I can now say that I have found out this as well as this. So I will now pack them in a column. And so there are two mass transfers operating, the external and the internal. And then I will sort of try to find out the phi values at different parts of the column, and they will be changing. And so that is there is a serious issue here. And then I can find out the Biot number, which is phi tan phi. And I don't know whether I mentioned this or not. I think I did mention it very, very briefly. I didn't derive it upon dA. So remember that these are changing, dA and phi and all are changing. And it is interesting that you will discover how the Biot number changes across the column. Notice that both mass transfer, internal mass transfer as well as external mass transfer will tend to become more dominant as the column moves up, because substrate concentrations tend to decline. As the substrate goes up, the substrate, the bulk will be low. So if this is low, then this is also low, and then inside is also low. So both are declining. Do the relative contributions of internal and external mass transfer change as the column goes up? Does the Biot number change? This is an interesting question that I leave you to answer. It is not an easy question. Okay, so when we work in industry, we work with both external and internal mass transfer. We have to take a decision. Now you can imagine how complex a problem this becomes. Not a complex problem. What a nice optimization problem becomes, because now you want high velocities, because you want to take care of dA, and you want smaller radius because you want to take care of phi, and the smaller the radius and higher velocity will make trouble for delta pressure drop from the Kármán-Kozeny equation, which you said you people have not heard of, but you know, you can well imagine fine beads and high flow rates will lead to high pressure drops, and you can't afford that, and you want tall columns, high velocities. And so this is a very interesting design problem of what kind of immobilized column you should make, what size of beads you should make, when you set up an enzyme reactor. And this is of course for the simplest case of V is equal to V max S upon Km plus S. These things become much more complicated, and this is where, I thought I would do all these things, but it's almost impossible. These are the kind of design problems that an IIT engineer is supposed to solve. Design an immobilized column. Choose different radius values, choose different heights, choose different velocities, and solve what is the most optimum design. This would be a 3-hour, 4-hour problem. One question, one end semester exam. But I am not allowed to do this anymore. I'm told that even with open book exam. This is the kind of problem that is a real, genuine engineering problem. You should learn how to solve design problems, even if you don't learn it now, because because of the pressure of your colleagues, which tends to push the class down in terms of its quality. At least you people should be aware that these are the kind of problems you need to solve. These are the kind of problems you need to solve. And then, of course, more complicated stuff. I mean, I'm sort of mentioning this because I want you to be aware that we are doing a very simplified picture. So I'm mentioning this because then I want you to be aware that not only this, but of course, different forms of reaction. Most of the reaction kinetics are reversible. A to B goes back, just like I sort of go. So this reaction equation changes. Now, hold on. How does it change? Okay, sorry. Let us go back. Let us not go back. Let us say that this is the kind of equation I am using, V max S upon Km plus S. V is equal to V max S upon Km plus S. Now I have a reversible enzyme kinetics. Can I represent this reaction in the same way as I wrote a Michaelis-Menten kinetics, but with some Vm star, with some S as S star and some Km star, just like apparent we did plus S star? Is it possible to represent it like this? So that the kinetics or the whole mass transfer, external mass transfer, internal mass transfer, the thing that we solved essentially does not change in its formulation. Instead of using Vmax and S, we use S star, Km star. For example, let me say this, and you will obviously understand. When does this reaction go to 0? Hello?
Sir, when S goes to 0.
When S goes to 0. Okay. When does A to B reaction go to 0? When A का अगर S हो तो? When S goes to S equilibrium.
Yes, sir. S equilibrium, sir. Yes, sir.
ठीक है ना?
Yes, sir.
फॉलो कर रहे हैं आप?
Yes, sir.
अदरवाइज फास्ट रहता है, 0 चला जाता है. ठीक है ना?
Yes, sir.
Is it possible? Is it possible that I can write S star as some kind of V max star S minus S equilibrium upon Km star plus S minus S equilibrium? Well, this is S star. ये मैं आप लोगों के लिए छोड़ता हूं एज अ क्वेश्चन. आप समझ रहे हैं मेरी बात?
Yes, sir.
इसका ओरिजिनल फॉर्मुलेशन क्या है? इसका ओरिजिनल फॉर्मुलेशन तो आप लोगों को याद होगा. इसका ओरिजिनल फॉर्मुलेशन है V is equal to V max 1 minus rho S upon Ks upon 1 plus S by Ks plus P by Kp. ये है ना?
Yes, sir.
शायद हाँ, इसको सिंप्लीफाई हमने ये सवाल अभी किसी से पूछा तो उसने कहा भाई ये V max हो गया स्टार. ये तो नॉनसेंस आंसर है ना. दिस इज कंप्लीटली रॉन्ग बिकॉज रो कंटेन्स S here. Yeah, रो इज व्हाट? रो इज S upon P. Okay, rho is S upon P. Rho is S upon P upon K equilibrium. When K equilibrium is actually,
Yes,
sorry,
sir.
P upon S. क्या बोल रहा हूँ मैं? गलत. P, which is P equilibrium upon S equilibrium. And P is nothing but S naught minus S. And S is whatever it is. And P equilibrium is nothing but S naught minus S equilibrium upon S equilibrium. And therefore this is S. And this P is nothing but S naught minus S. And this is of course S. And Kp is again in terms of equilibrium held in relationship. So is this whole complicated thing reducible by some clever algebra into this form? Where Vm are constants. Now the Vm should not contain any S term. It can contain S naught term, it can contain K equilibrium terms. Km can contain Kp terms. But it should not contain S terms. And the S star should be something like, as I said, S minus S equilibrium. In which case, if I am able to formulate it like this, then I can apply my mass transfer equations, external mass transfer, internal mass transfer equations to this kind of equation as well, simply using this kind of V as my formulation. Are you getting this? Or is it too complicated? आप लोग वापस जाके ये सवाल प्रैक्टिस करिए.
ओके.
ये रिजॉल्व करिए, है ना? देखिए क्या आता है.
यस सर.
ठीक है? Let us so you have now your sort of sets of exercises. I have given you internal mass transfer, external mass transfer, both methods, column internal mass, external mass transfer, CSTR. Both have different kinds of solutions. One has an integral solution, the other has a steady state solutions. Okay. So yes, I think let me stop here. And tomorrow there is the final class. I think Saturday is a working day. So we will reverse it, and Monday is the last practical day. So I think we will stop on Monday, unless you want an extra class on Tuesday as well. Tomorrow, please come and ask your questions.
So there is no class next week.
नहीं, मैं क्लास लूंगा, मतलब मैं क्लास लूंगा, but they will only be tutorial style classes, because I have a feeling that if I teach something new, it is just going to put pressure. For example, when I talked about all this, I really want to know what is happening in the CSTR. मैं जानना चाहता हूं कि क्या हुआ ये CSTR में हम लोगों ने उसको सॉल्व किया Km के टर्म्स में. But suppose the dilution rate is high, D is high, in which case S is high. S in, S out is pretty high. If S out is pretty high, then please remember that phi is no longer greater than 20. Maybe phi is greater than 2. In which case you can use the approximation, n by is equal to 3 by phi square, phi minus 1. But suppose phi is not even, 2. But suppose phi is not less than 2. Suppose phi is 1. Then you have to go back and write your COT equations. Remember your what was phi defined as? Hello? Yeah? नहीं याद है.
One second.
What was it? What was phi? Or what was? So 3 by phi square, and instead of cot minus 1, what was it? Phi, cot hyperbolic phi minus 1, right?
Yes sir.
Remember this efficiency?
Yes
तो
sir.
ये कब ऑपरेट करेगा? तो इस बेसिस पे करके आप दिखा सकते हैं कि at what dilution rate, for example, I start asking the question, at what dilution rate efficiency is equal to 80%? At what dilution rate efficiency is equal to 50%? Suppose I change the question. At what dilution rate efficiency is equal to 20%? So which approximation you can use will depend on the phi values. For efficiency values very low, very, very low, and 5% efficiency, you can very easily make this assumption. ठीक है ना? 3 by 5. Efficiency 3 by 5. So you notice that if it's greater than 20, 3 by 20 is, 3 by 21 is 1/7. Less than 10%. 5%, etc. But what happens when the efficiency is 80%? When is the efficiency 90%? When is the efficiency 80%? At what dilution rate? Then you have to solve this equation in terms of phi and cot phi. Why did I derive this? Because that is the correct answer. And what is the profile inside the cell? These are also important questions. What is the profile inside the cell? So, let us also understand the system in its microscopic behavior. So if I have this problem here, this is the cell, and this is the sort of diameter. So then obviously here the concentration S is here, some value here, and at this point it is like this. Now tell me what is the profile? So for that you have to remember your basic derivation equations. Do you remember? Because we then did not integrate it, but we had that and this slope here is what we use. We use this slope here and matched it with the fact that there is no accumulation inside the column of substrate, and said that this slope here of this function of this profile function, this is the profile inside, this is the substrate profile inside, this is the substrate profile inside the bead. So given the substrate profile inside the bead, we took the derivative of the substrate profile at R is equal to R, and that was the matching rate of substrate coming inside, and that is how we found out the net rate of reaction. That's what we did, right? We did a clever thing. We did not integrate this.
Yes, sir.
We did not integrate this profile. We simply found out the derivative of this profile and multiplied it by the mass transfer coefficient, because we know that the rate of substrate coming in is equal to the rate of reaction inside the bead, because the bead is not building up with the bead. In that sense, is in some notional steady state. There can be no accumulation inside the bead, right? So
Yes,
what
sir.
is the profile? Yeah, so at high dilution rates, how do the profiles look like? What are the efficiencies? Okay, what are the efficiencies here? At 80%, 50%, when are the efficiencies 80, 50, 20, etc., etc.? These are questions also you need to answer. Go back and do these problems.
Okay, sir.
Okay, so let us stop here, and tomorrow class, shall we continue this or shall we do something else? Okay, we'll do something else.
Yes. Okay.
I hope you can solve these problems. Okay, thank you.
Thank you, sir.
Thank you.